Thank you. And shall we start this too? Sorry for the small logistics issues. So I'm Rafael Martinez. I'm from the CFA. And I want to talk a little bit more about the issue of light curve classification, especially in the context of supervised learning and the issues that arise when you depend on a training set. This is, in the context of the SAMSI working group 2 that she's talked about earlier, and also in the context of trying to come up with a data challenge that we can issue for the community to bring their own classifications ideas into the problem of classifying light curves. So, well, the motivation and the reason why we're all here, part of the reason why we're all here is because astronomy, of course, is entering into the time domain frame. And the LSST will be coming online in 2021. It's currently under construction in Chile. It has an 8-meter reflector. And the idea is that it will basically take an image of every part of the visible sky from Chile every few nights in 6 different bands, which was one important thing that I think didn't necessarily get mentioned before, for a period of 10 years. And what you see here is a little simulation of what the first year of observations may look like with the color indicating the number of visits that each patch of the sky will get. And this is around 20 visits for the heart. And that will, of course, give us an opportunity to study transients. And in particular, because it will go deep and it will go long, we will be able to maybe discover new types of traces that we have not been discovered yet. But of course, there's the challenge and the fact that each periodic source is different, and we have different types of variability in the sky. So we can have something like the Cepheid or RR Lyrae that are periodic in the sense that they are consistent in their periods and amplitudes, so you can easily model them. They are usually used as standard candles, so they can be used to estimate distances in the universe and are very important for cosmology studies. There are also quasi-periodic variations like Mira stars, where they are dominating frequencies, but there is no consistency in either phase or amplitude or both. But of course, there are also things that are not periodic at all, or that you don't expect to be periodic, such as AGNs and QSOs that basically vary without any obvious pattern, and transients that have like a peak of intensity and then go down again, like supernovae or stellar flares, etc., etc., etc. And if you see, the light curves of each of those things look different. And of course, the 2 challenges that we have is, one, design the survey so that we can get as much information as we can from the observations we take in the different filters at specific times. But also we have the issue that once we decide on the design of the survey, we need to do the best we can to classify the sources and assign them classes and labels. And that's more or less what we've been thinking about in the working group 2. So why is this a challenge? Of course, it will be a challenge first because there will be massive amounts of data coming up, the order of 10 to the 9 sources for which we will have light curves once LSST comes online. And of course, that's problematic not only because of the volume of the data, but also because, as has been mentioned before, they are sparsely sampled. So they are not sampled at regular intervals, and also they are very sparse sometimes. So there's big gaps between the data points here, as in this example here. And there's also the fact that in the particular case of the LSST, the observations will not be taken simultaneously in each filter. So you will have 6 different bands, and in each band, in principle, you have different properties of the variability. And of course, by design, LSST will only be able to take 1 filter at a time. So you have the additional challenge that you need to deal with things that it's taken in different filters at each time. So machine learning, of course, has come up as a very useful way to deal with this situation. Basically because you can learn basically what you do when you do machine learning, and one of the things you can do is learn functions that map a space of features of these light curves to a space of probability for different classes. And that's one of the things that you try to do with machine learning. But you can also do things like detect outliers. So find which light curves are the weirdest with respect to the population. But one issue with those, and this is the general idea of how such machine learning algorithms work for the case of supervised learning. So you have a training set of light curves for which you can extract some features, and those for each of the sources you have a vector of features. And then you also have the labels for those sources. And you have your machine learning algorithm that can be, random forest classifier, support vector machine, and an artificial neural network that basically tries to minimize a loss function to find, to optimize the parameters that weight these different features and decide which features are more important in deciding which source belongs to which class. And with that, you can have a predictive model to which you enter your new data. So once you have trained your algorithm, you can enter a new light curve with a feature vector, and your predictive model will give you a posterior probability for the different classes. So you can, in principle, say which source belongs to which class. But there are a number of ways in which this process can go wrong if you don't do it properly. And I think this is one of the main challenges that the machine learning community faces. The first thing has to do with the training set itself, because it can be biased. For example, you can have a training set that is biased towards the brightest sources, because they are the ones that are easier to assign labels to, either because you can take spectra for those sources or because they're closer and they're brighter. So you can, it's biased towards those types of sources. And also, rare classes can be underrepresented, so which is related to the previous point. So you can have a bias in the training set, and of course, if you assume that the training set is representative of the population on which you're going to test your machine learning algorithm, then you might end up with catastrophic mistakes in the way you get your labels. But also, feature extraction can be a complex issue, because, as was mentioned before, well, features will depend on the types of sources that you want, and the best features for one type of variability might not be the best features for other types. It's also, the features are also depending on the noise, they are depending on the time sampling of your light curve, and on top of that, usually feature extraction is computationally expensive. So if you want to do this for many sources, you are in trouble, because you will have big clusters, or maybe not even a big cluster can do that for you. The labels, of course, are another issue, and this is related to what I was mentioning before. How do you determine the actual ground truth classes and labels for your different sources? Also, it can happen that you have good labels, but that come from a different survey with different properties of sampling or with different telescopes, and you might want to try to leverage the information that you have from other sources in order to do your classification of your new survey. So assigning labels is also problematic, and that's one of the ideas that I want to discuss here is to what extent we can use probabilities in the training set. So that's the question I asked before. If you don't have labels, but you have probabilities of one source in your training set being of this or that label, how can you incorporate that into your training process? So this is an example of such training set bias. This is an example from a paper by Richards a few years ago, where you have here two space of 4 features, a period amplitude space, and the QSO-like variability and the significance of the first frequency. And in this case, this set of data from the HIP and OGLE catalogs was used as a training set. And then the test set was the ASAS for variable stars. And you see that there are significant discrepancies between the training and the testing set. In particular, for example, the test set has higher density of short period, high amplitude variables. And so this is an important problem that sometimes when people apply these machine learning algorithms don't take into account. And I think we have to be very careful about how we design a training set so that it actually represents the data we want to do that. How can we go about this bias? What can we do to improve our training set? There are a number of possibilities, and I'm just mentioning a couple of them here. So one possibility is to do active learning. So you can basically, once you have your trained algorithm and you apply to a test set, this is an example from a color plot for young stars, and you have something that gives you discriminators between the two. There will be some, once you apply that to an unlabeled test source, maybe that you can pick the test source that are unlabeled that will improve the performance of the algorithm the most. And so you can select, for example, sources that are very close to whatever boundary you have here, and you can follow them up by, for example, taking spectroscopic observations. and then you can include them in the training set in the next step. So that way you can, start to select the sources, the test sources that will improve your training process and incorporate them into the training set. One other interesting idea was also mentioned by Ashish, and I hope this will get discussed a little bit later in the meeting. It's the domain adaptation. Basically, when you have a previous survey on which you have defined your discriminator hyperplanes here that separate your different classes, and then you have a new target survey where you only have labels for a few of them, you can in principle try to find a transformation of these hyperplanes that separate the sources in your well-known catalog to transform them into the hyperplanes that separate the sources in your new target, so that you can, by training using all these sources plus the few on which you have labels here, you can come up with a new hyperplane that will separate the different sources and this. And this is another interesting way, with the advantage that you will only need a few fraction of the sources for with labels in your set of interest. So, but of course we need to get started somewhere, and so we've been trying to construct a training set for which that we can use in this future data challenge, where people will be able to apply their classification schemes. And we've chosen the SDSS stripe 82, which is a stripe here along the galactic equator that has the advantage that has gone a couple of magnitudes deeper than the standard SDSS observations, but also has a lot of ancillary data at many wavelengths. So you can have additional information all the way from the ultraviolet into the radio, and it's an interesting set to try. And of course, the SDSS has 5 filters, which makes it similar to in this multiband aspect with LSST. Some basic facts about that. So it's 5 bands, about 60,000 sources, about 50 observations per band, but there's a significant variance in that number. Photometry is roughly, but not exactly, simultaneous across different bands. It's deeper, and there are also variability in cadence, but on average, every 2 days, you get a new observation of each of these sources. And here's some examples of different types of variables in the time axis here and here. Once you fold it into the phase space, and you get the different types of variability. These two are periodic. This one is a quasar, which does not have a period, or not necessarily has a periodic behavior. And of course, the first thing we did, we tried to merge existing classifications for these data sets. So we went, because you can find the light curves online, but not for all of them you will have labels. So you want to try to find labels. And there's a number of methods in the literature for assigning labels to these sources. So for example, for the RR Lyrae, you can do a little bit of color selection to select your variable stars. And then you can do some template fitting for the light curves and separate further the space by plotting here the magnitude, the G magnitude and the variability of G magnitude, and you will separate the sources of your interest. For the eclipsing binaries, you usually do spectra, and you do visual inspection of the light curve in order to decide whether it's an actual eclipsing binary. The high amplitude delta Scuti stars, there's been some efforts to do visual inspection plus principal component analysis on the colors, and also do a random forest classifier. And this is where my question comes. I mean, if your labels come from a previous classifier, how can you use the information of that previous classification that gives you probabilities rather than specific labels in order to incorporate that in your training process later? And of course, QSOs are usually done with spectra. You can spectroscopically confirm them. So once we've done that, we are trying to do the feature extraction for resources. And the first thing you want to try is to try to find periods for the different curves in your set. So we're using this interesting approach that uses the multiband periodogram. So basically, we have the usual Lumskargel idea in which you basically phase your light curve and assume that once you have folded in the phase space, it will have some behavior that is sinusoidal, and you make a fit of a truncated Fourier transform for that with a number of terms. The more terms you use, the better your fit, and you get periods. But you could also do it using all the information contained in the variability of the different bands. So you will have, in this case, one component that deals with the overall variability of the source in all bands together, and then one term that accounts for the shift or the offset of the different bands with respect to that overall variability. And in that paper by Van der Plas and Ivesic, you can find that this method is pretty interesting in that, at least when applied to simulated data, in that and of course there's a point there regarding what happens when we apply it to real data, but when you apply the standard periodogram with each of the different bands, you get nothing from the periodogram, so there's no clear peaks in the power spectrum of the different periods. Whereas when you use this approach here, you can recover the actual frequency, at least multiples of the actual frequency here, that in this case was around here, by using that. And the advantage of that is that this is linear on the weights of the different components here. So it tends to be fast, which is something you want. As I said, feature extraction can be something that takes ages. So this is an interesting thing. And you can use a number of methods to avoid degeneracy on the determination of these parameters by using some regularization approaches. So basically by assigning a prior on those thetas, so you get something that is not degenerate. These are some of the results from applying that periodograms to some of the Stripe 82 sources. This is together with James Long and a student in Texas, Virisha, who has done the period finding and then folded some of the light curves in the LSST. So we're currently doing it on all the sources. We have 60,000 sources to try to estimate the periods and have that period taken account for. But the last thing I wanted to discuss today was what happens and what if you happen to not have any labels? I mean, what if you want to get rid of the labels either because you don't trust the labels or you want to do something different? For example, you want to find outliers. So there are some interesting recent ideas on how to do unsupervised machine learning on this kind of data sets, and this idea by Baron et al. This year is a very interesting one that I've been trying to apply to this data set. So basically the idea is that you have a space of features. This is only a demonstration. You have a couple of features here, and you have your original data that has some correlation between those features, and you have your marginal distributions. So you can actually take those marginal distributions and sample, draw samples from those marginal distributions to create another synthetic data that has the same marginal distribution, but that does not show the correlations that you see in the actual data. And then this is when and so far you're not using labels for them, but you turn this kind of unsupervised into a supervised problem by now labeling this as real data and labeling this as synthetic data, and do a random forest classifier to try to distinguish between the two. And basically what it will do is it will try to find the sources that are actually correlated, and it will find the sources that are from the real data set. And this is a probability plot of what is the probability of sources being from this type. And you see that the classifier can actually find that. But the interesting thing is that then you can define a distance measure on this classification by looking at how separated the different sources were in your decision tree, and you can kind of find a distance measure between different light curves in your classification process. So you can, in principle, find sources that are very far in this distance measure from the ensemble, and that will allow you to find light curves that are weird as compared to the general sample. And this is something that I recently applied to a data set of Kepler light curves just to try it. And this is an example of what we get. So these blue plots here are basically the weirdest light curves that you get. You see that in some cases you get very, very strange variability patterns. And of course, in this case, it was easy because the light curves in Kepler were equally spaced in time, and they were also normalized. So the idea is we want to translate that into something that works also for, in order to find outliers in light curves that are not necessarily equally spaced in time and that are not normalized. But there are some promising ideas. In fact, one of the weird objects that we were able to find using some of these methods was this planet that people have been claiming that has some kind of extraterrestrial structure around it because it has a very strange light curve. So not all outlier detector methods are able to find it, but some of them actually do that. So I just wanted to leave you with some additional questions regarding this problem I've presented here. So one thing is, in terms of the data challenge that we're planning to do, so can we try to leverage results from other existing surveys that have already labels, for example, the Catalina survey or whatever, in order to try to propose people to do a domain adaptation challenge? So do we want to try people to try different domain adaptation techniques to do classification on either our data set or in the future with LSST? In terms of active learning, does it make sense to try to do follow-up to some of the sources we have, for example, in the Stripe 82 data set, to try to see if we can improve the performance of the existing classifier by following up certain particular sources and doing spectroscopic observations of them, for example? What about period finding? Do we believe that this is a promising approach? There are other ways to find periods, and we should make sure that we use the appropriate or whatever that is fast and accurate, and that might be difficult to find, as Matthew can tell you about. And also, of course, how long, in principle, if we want to do classification of the LSST curve, an interesting question is how long do we need to wait along the survey before we can actually start being confident of periods and of labels assigned with the classifiers? How many data points we need to do that to have before we can actually apply all these methods to the data set? And I think this is what I have, so I'll leave some time for questions. Thank you.
In reference to your second point,
the
follow-up from being Stripe 82 spectroscopy, could anything be gained by doing, looking at Stripe 82 in other light event surveys in terms of classification there, in case that would give more information?
So try to look in other surveys for which...
Well, I mean, either Catalina, which has come Stripe 82, or, ZTF is looking for things they need to be doing commission. Would a ZTF survey of Stripe 82 help with active learning in some ways like that?
Right.
I get the idea about doing it from spectroscopic follow-up, but is there some way we can use other light curves to help with active learning, which would then feed into LSST more directly?
Yeah, I guess it doesn't have to be spectroscopic. I mean, this is a natural way to do it for some types of sources, but it's also consuming in terms of telescope time. So yeah, in principle, whatever works. I mean, one idea that I had is try to match the Stripe 82 catalog with, for example, the Richards catalog that has probabilities of the sources, and try to use that. But then again, I'm stuck with the idea of how do we incorporate a probabilistic training set into a training process. That's something that I've been trying to think about a little bit, and if anyone has an idea of that. So if in your training set you don't have specific labels, but rather a probability, a posterior probability, how can you incorporate that? But yes, in principle, whatever that gives us a degree of certainty on the labels for these sources, especially for those sources that fall close to the hyperplanes that separate sources, that would be absolutely useful. Yeah.
Tests that you talked about. So you seem to have done some amount of tests by using pure photometric data. Mm-hmm. So, but some of those objects would have spectroscopic data. So how do the outcomes of the purely photometric
compared to the spectroscopic?
When you put in the spectroscopic?
Yeah, that's a good question. And I don't think we've tried to look into that. Certainly for some of these sources, we will have spectra. And you would hope that your photometry only classifier would agree with the spectra. But that's something that we have not yet done.
So you used the Lomskagel method, and I think they were irregularly sampled data. So yes. I was wondering how you would respond to the point that Jogesh raised earlier. I mean, he's been raising it for many years about that being a problem with using that methodology.
I don't recall what exactly the point was there. I mean, I think the one of the main downsides of this method is that it actually assumes that the light curve looks like some kind of sinusoidal pattern. And of course, that can be improved as you add more and more components to the truncated Fourier transform. This method of using the multiband at least seems promising in that it is able to incorporate all bands and predicting the periods right, at least for some of the simulated sources. But as some people have pointed out here, when you deal with real sources, then you're in trouble because the noise is different or whatever is different. And that's why I was bringing up the idea of trying to do this with simulated data and then incorporate the noise. But for that, we need to incorporate a pattern, a noise pattern that we actually understand, which is the other part of the problem. I mean, you could use simulations, but then you would need to understand the noise that you add to them for doing it. So I don't believe that this is necessarily the best approach. But it's a first attempt to try to compare what we have with what's out there and see if we can standardize the process for as many sources as we can in the training set.